So I want to do this overview because I want you to really understand the assumptions, and one way to understand how specific the assumptions are is to really see what are all the possible options of assumptions that we have, okay? Or the diversity of the assumptions that we could have, okay? Let's start with the first one, A1, that the model is linear. Y is equal to beta 0 plus beta 1 x plus epsilon. I'm not going to cover this, but of course, the model doesn't have to be linear. Could be quadratic, could be all sorts of things. The true model doesn't have to be this, okay? So it's very easy to come up with alternative assumptions. So alternative assumptions are easy to think of. Let's go to A2. A2 is that the sample is random. Let me try and explain what that is really telling you. What that's telling you, it's telling you that the yi and the xi are independent of the yj and the xj. In other words, one data point is completely independent of the other data point. This thing here will imply things like that epsilon I is independent of epsilon j for all i's different from j. Okay. What this will kind of imagine that I told you that the A1 assumption holds. So this is the true line. Beta 0 plus beta 1 times x. Okay. And imagine that you observe that the true population values were like this. And then you had a few of these things kind of laying around. Okay. Imagine that, so basically I'm telling you that A1 holds, okay? A1 holds. But you see this. What does this pattern tell you? What does this pattern tell you? Well, this pattern violates assumption 2 of random sampling. How do I see that it violates assumption 2 of random sampling? Easily. If this epsilon here, this is the error term, right? The deviation away from the true line. If that is positive, how likely is it that the next epsilon to be positive as well? It is likely because of this shape that the data has, right? The data kind of goes like this, which means that the error term and the different data points here are correlated with one another. They're dependent with each other. Okay? The assumption A2 of random sampling really tells you that the different data points are independent of one another, okay? The epsilons are independent of one another. So the fact that you know epsilon 1 doesn't give you any information on what epsilon 2 would be, okay? Those are completely random. So understand that this assumption 2 is quite crucial, but it really boils down to this idea that epsilon 1 and epsilon 2 are not random, okay? And so epsilon 1 and epsilon 2 are independent, sorry, not non-random. They are random, but they're independent, okay?
Does it violate assumption 4 as well?
Does it violate assumption 4 as well? Well, it doesn't have to, right? This error terms, the expectation of the error terms could well be equal to 0 here, right? Because you have some of them that are positive and some of them that are negative, right? So on average, those error terms could be all equal to 0. And I drew it in such a way because I didn't want to violate that assumption 4, at least not immediately, okay? So in that graph, assumption 4 could also hold. So the expected value of the epsilon could still be 0, okay? Expected value of the epsilon could still be 0. It will likely violate assumption 5, however, because knowing the x's will give you something about the value of the epsilon, right? So if the x's are between this point and this point, your epsilons are likely to be positive. The expected value of the epsilon is positive. So this thing here would generally violate A5 as well. Okay. So this is the A2 assumption that the sample is random. The A3 assumption is something that I will not discuss because the A3 is what you need. The A3 is what you need in order to carry out the OLS. There is no variation in this. You either have this or you don't have this and you cannot do OLS. But in 99.9999% of situations, unless you run into a dummy variable trap, A3 will not be a problem. As a matter of fact, you can go as far as saying A3 maybe is not an assumption, it's just a condition that we need. Okay, so A3 is it's quite standard. Note what A4 is telling you. A4 is telling you that the expected value of epsilon I is equal to 0 for all I. Here's the door. So assumption 4 is telling you that if you have a sample of n observations and you have n epsilons, what assumption 4 is telling you that the expectation of the first epsilon is equal to 1, the expectation of the second epsilon is equal to 0, is equal to 0. All this expectation of every single individual epsilon is equal to 0. How can we violate this assumption 4? Easy. You could violate assumption 4 by simply having this nth one equal to 2. There is nothing that prevents every single epsilon to be different. In fact, you could have an assumption that says this is 1, this is 2, this is 4, etc., 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 where you have different expectations of what the epsilons would be for different observations. Okay? It could be that each of those epsilon is different, has a different expectation. So when someone says, how can you violate assumption 4? What you could also violate it with something that looks like expected value of epsilon is equal to C for all i's. And then what you're saying is that all of this are equal to C. But this is only one possible violation of that A4 assumption. Okay? You could possibly have all of those observations be different. Okay? So we have done some exercises with this A4 violations, okay? A5 tells you that the expected value of epsilon I conditional on the x's is equal to 0, or is equal to the expected value of epsilon I, which by assumption 4 is also equal to 0. This is telling you that the mean of the epsilon is unaffected by your knowledge of the x's. Okay? So on average, the epsilons are still going to be around your population mean even when you know what the x's are. What could be variation of this? It could be weaker versions of this. A weaker version of this would be to simply say the epsilons and the x's are uncorrelated. Okay? This is a much stronger assumption on the relationship between the x's and the epsilons. Let me talk about the final one, A6. Variance of epsilon I conditional on x, or treating x's as fixed, is sigma square for all i's. What this is telling you is that variance of epsilon 1 conditional on x is equal to sigma square. Variance of epsilon n conditional on x is equal to sigma square. How can I violate this assumption? This is called homoscedasticity, equal variance. How can I violate this assumption? Easily. I can easily violate this assumption by just changing one of this and saying this is equal to 2. And this 2 is different from sigma square. But note that it could be that all the variances of all the data points could be different. So you could have had 1, 2, 3, minus 11. No, variance cannot be negative. 10, etc., etc. You could have had different variances for every single error term. Okay? You could have had situation where you could have said, well, actually, the first half of my observation have variances of 2, and the second half of my observations have variances of 100. How would that look on the graph? That on the graph would have looked like this. Maybe all this observation with x is below here. Let's say this is the true line. Will have relatively low variance. But all the observations with this other epsilon, this other bunch of epsilons, for whatever reason, have higher variance. Okay, Okay, that would be a violation of the A6 assumption. So, in summary, you're going to see a lot of these assumptions, A1 to A6, coming out in all different shapes and forms. Most of the shape that we're going to use is this classical A1 to A6. That's the shapes that we're going to use. But it's important to understand how do they manifest themselves into a graph so that you know when they're violated, and also to understand that there are different shapes and different versions of these assumptions. Okay. So with that note, I will stop here.